Hello friends, how are you? Hope you all are good and doing well. In this video lecture, we are going to learn about a topic which is different from the normal, that is real world. That means we are talking about the something that is not real only, but it is including the imaginary things. That means we are going to talk about the things which include real as well as the imaginary world. That means we are going to discuss about the complex numbers, complex systems and quadratic equations which solutions gives not only real but also a complex number. So friends, myself Virendra Kumar and you are watching Sciacademy channel. So let's start the video lecture. Friends, as you know that the quadratic equations give two solutions, and if their discriminant is less than 0, then in that case the solution may not be real, that becomes imaginary. So how can we deal with the imaginary numbers? Mathematically we will learn about those things in this lecture. So let's start the lecture by denoting the square root of -1 by the symbol I. This symbol is known as iota. So we have I square is equal to -1. This means that I is a solution of the x square is equal to -1. X square is equal to -1. A number of the form a plus ib, where a and b are real numbers, is defined to be a complex number. So any complex number we denote by z, and it is equal to a plus ib, where a and b are real numbers and I is the iota given by I square is equal to -1. So for example, let us take 2 plus I 3, -1 plus I square root 3, and so on, where in this 2 plus I 3 is 2 and 3 are real numbers. So the complex number is denoted by z is equal to a plus ib. That means it is including the real as well as the imaginary part. So we write the real part, real of z is equal to a, and imaginary part, imaginary of z is equal to b. Now the two complex numbers, suppose z1 is equal to a plus ib and z2 is equal to c plus id, are given and we want to equate them. So how can we equate them? So for that we will equate the real part of the two complex number and imaginary part of the two complex numbers separately. That means in this case we will equate a is equal to c and b is equal to d. To understand it clearly, let us take the example number 1. Excuse me. If 4x plus I into 3x minus y is equal to 3 plus I into -6, where x and y are real numbers, then find the values of x and y. So it is given that this, and we have to find the values of x and y. So what we will do, we will equate the real part and imaginary part separately. So in this case we see that 4x is equal to 3 and 3x minus y is equal to minus 6. Therefore this, and from this we can get x is equal to 3 by 4 and y is equal to 33 by 4 after substituting the values of x is equal to 3 by 4. So now we will deal about the algebra of complex number analogous to the algebra of the real numbers system. As we know that in the real number system, the addition of two real numbers, multiplication of two real numbers follows some set of rules. In similar to those things, we will see in the complex number system that they also follow the some rules of addition and multiplication. So let us check that. So addition of two complex numbers. Suppose there are two complex numbers, z1 is equal to a plus ib and z2 is equal to c plus id. Then if you want to add them, then how can you add that? So for adding them we have to add the real part and imaginary part separately, and then we can do that by this. Now suppose you want to add these two numbers, 2 plus i3 plus minus 6 plus i5. So 2 and minus 6 will give the minus 4, and 3 and 5 will give the 8. So the addition of these two numbers will give minus 4 plus i8. So there are some set of rules which are followed by the complex numbers in the addition of two complex numbers. So first rule is the closure law. So closure law means if we are adding two complex numbers z1 and z2, and then if the result is also a complex number, then we will tell that the addition of the two complex number is closed. That means it follows the closure law. Similarly, for any two complex numbers z1 and z2, if we are adding z1 plus z2 and it is equal to z plus z1, then we will tell that it is following the commutative law. That means two numbers are commutative in addition. Similarly, the associative law, for a given any three complex numbers z1, z2 and z3, if z1 plus z2 plus z3 is equal to z1 plus z2 plus z3, that means they are following the associative properties, then we tell that the complex numbers are following the associative law. Similarly, there exists additive identity in the complex number. That means there exists a 0 belonging to complex number z. That means if we add 0 plus i0 with any complex number, the result will be the same complex number. Right? Similarly, there exists an additive inverse in case of the complex number. That means for a given z is equal to a plus ib, there exists a number that is minus a plus I minus b, and in such a way that if we add this z is equal to a plus ib with this number, the resultant will be the additive identity, that means 0. So that means z plus minus z is equal to 0. Thus we see that analogous to the real number, complex number also follows the set of rules of addition, that is closure property, commutative law, associative law, and there exists also additive identity and additive inverse. Similarly, we can prove that the difference of the two complex number also follows this set of mathematical laws. Now let us check whether the multiplication of the two complex numbers follows the set of these mathematical laws or not, that is whether they follow closure, commutative, associative properties, and whether there exists multiplicative identity and multiplicative inverse or not. So for the first closure law, before starting that, we will define how we can multiply the two complex numbers. Let us suppose that we are given two complex numbers, z1 is equal to a plus ib, z2 is equal to c plus id, and we want to multiply z1 into z2, that will be given by this. How this comes out? So we multiply these two complex number by this, that we multiply this a into c and then ib into id, that will give minus b into d, so we will get this number. And second, we multiply this plus ib into c and then plus a into id, that will give I into ad plus bc. So in this way we can multiply the two complex numbers. So let us check whether they follow the closure properties or not. So we can see that if we multiply the two complex numbers, their multiplication is also a complex number, that means they comes out a complex number after multiplication between the two. Therefore the multiplication of the complex number is closed. Similarly, we can see that multiplication of the two complex numbers z1 and z2 is commutative, that is if we multiply z1 into z2, that comes out to be equal to z2 into z1. And also they follow the associative law. For any three given complex numbers z1, z2 and z3, we can see that z1, z2 into z3 is equal to z1 into z2, z3. And fourth property, that there exists multiplicative identity, that is if we multiply any given complex number with multiplicative identity, in this case is equal to 1, that is equal to 1 plus I0. This is multiplicative identity for the complex number, and we multiply this value with any complex number will be equal to the given complex number. That means there exists there exists a multiplicative identity. Similarly, there exists a multiplicative inverse. That means for a given complex number there must exist a multiplicative inverse after. That means after multiplication with the multiplicative inverse with the given complex number will be coming out to multiplicative identity, that is 1 plus I0. So suppose that you are given a complex number a plus ib, so that means there exists a number 1 by z is equal to z to the power minus 1. That means if we multiplied z into z minus 1, the resultant should be equal to 1 is equal to 1 plus I or iota 0. Also, sixth property in case of multiplication of the two complex numbers is following the distributive law, that is Z1 into Z2 plus Z3 is equal to Z1 Z2 plus Z1 Z3. Also Z1 plus Z2 into Z3 is equal to Z1 Z3 plus Z2 Z3. Similarly, we can show that division of the two complex numbers, that is defined by Z1 by Z2 is equal to Z1 into 1 by Z2, also follow the set of these mathematical rules. So for example, let Z1 is equal to 6 plus 3i and Z2 is equal to 2 minus I, and we want to divide the Z1 by Z2. So how can you do that? We can do this by 6 plus 3i into 1 by 2 minus I. Similarly, that means we can write this by this. This is nothing but we are simplifying this. 2 minus I is equal to 2 plus I divided by 2 minus I into 2 plus I, and the denominator will be equal to 4 square minus I square, that is 4 plus 1, that is equal to 5. So we will get this, and finally we will get this and this. Now we will learn about the powers of iota, that we know that I square is defined is equal to minus 1. So what will be the value of I to the power more than 2? That means I cube, I4, I5, I6, I7, I8 and so on. So let us check. I cube can be written as I square into I, that is equal to minus 1 into I, that gives minus I. I to the power 4 can be written as I square into I square, that means minus 1 to the power 2, that is equal to 1. Similarly, we can define I5 to the power I to the power 5 is equal to I to the power 4 into I, and we know that I to the power 4 is equal to 1, that is equal to I, and so on. So now I to the power minus 1 means it can be written as 1 by I, and after simplification this gives minus I. Similarly, I to the power minus 2 can be written as 1 by I square, and that is equal to 1 by minus 1 is equal to minus 1, and so on. So in general, for any integer k, we can write I to the power 4k is equal to 1, I to the power 4k plus 1 is equal to I to the power 4k plus 2 is equal to minus 1, and I to the power 4k plus 3 is equal to minus I. So remember this relation. Now let us talk about the square root of a negative real number. So if you are given a negative real number, suppose this is minus 16, and you are asked to find the value of square root of this number, that is square root of minus 16. So how can you find that? So let us learn. Since we know that I square is equal to minus 1, that can be written as I is equal to square root minus 1. Similarly, minus I to the power 2 can be written as I square, that is equal to minus 1. That means the square root of minus 1 are I and minus I, that is square root of minus 1 can be written as plus minus I. However, by the definition we only take the plus I. Now we can see that I and minus I both are the solutions of the equation x square plus 1 is equal to 0. So let us check. Suppose you are given square root 3i whole square. That can be written as square root 3 square into I square, that is equal to square root 3 whole square is equal to 3, and I square is equal to minus 1, that is equal to minus 3. Similarly, minus square root 3i whole square can be written as minus square root 3 whole square into I square, that is equal to minus 3. Thus we see that square root of minus 3 are plus 3i plus square root 3i and minus square root 3i. So we see that the square root of minus 3 are square root 3i and minus square root 3i, but as per the definition we will take only the square root 3i as the square root of minus 3, that is this. So till now we are finding out the square root of the negative real number. So in this case we are getting the two values, but what we will do, we will take the positive value only, that is we will take this. Now generally if a is a positive real number, then we write square root minus a is equal to square root a into square root minus 1, that is equal to square root ai. What about the product of the two square root? So we know that this can be written as this for all positive real numbers a and b, and this identity holds true if any of the two real numbers is greater than 0, that is either a is greater than 0 and b is less than 0, or a is less than 0 and b is greater than 0, then this identity holds true. But what if both are less than 0? In that case we will see that, suppose we are taking I square is equal to like this, square root minus 1 into square root minus 1. As per the definition, I is equal to square root minus 1, and we see that square root of minus 1 into minus 1 can be written as this 1, which is a contradiction of the fact that we defined iota is equal to square root of minus 1. That means the square root a into square root b can't be equal to square root ab if both a and b are negative real numbers. So this identity to hold good, one of the two real numbers should be positive. And further, if a and b is 0, any of the a and b is 0, then this product is 0. Now identity square of z1 plus z2 can be written as z1 square plus z2 square plus 2z1 z2, such as in the case of the real numbers. So let us prove this. So this z1 plus z2 whole square can be written as the product of z1 plus z2 into z1 plus z2. Now multiply these two. So z1 plus z2 into z1 plus z1 plus z2 into z2 by the using the distributive law, and this z1 into z2, z1 into z1 becomes z1 square plus z2 z1 and plus z1 z2 and plus z2 z2 square. By the principle of commutative law, this becomes equal to 2 z1 z2, and thus we see that z1 plus z2 whole square is equal to z1 square plus z2 square plus 2 z1 z2. Similarly, we can prove the other identity like z1 minus z2 whole square is equal to z1 square plus z2 square minus 2 z1 z2, z1 plus z2 whole cube is equal to z1 cube plus z2 cube plus 3 z1 z2 into z1 plus z2, and z1 minus z2 whole cube is equal to z1 cube minus z2 cube minus 3 z1 z2 into z1 minus z2. So we can prove all this identity. So let us solve the example number 2. Express the following in the terms of a plus ib. So we can do this minus 5i into 1 by 8i. So how? Let us write this, and minus 5i into I is equal to minus 5i square, I square is equal to minus 1. So minus 5 into minus 1 is equal to plus 5, that is equal to plus 5 by 8, and that can be written in terms of a plus ib, that is here the real part is 5 by 8 and imaginary part is 0. Similarly we can do this. Okay, now example number 3. Express 5 minus 3i whole cube in the form of a plus ib. So firstly we will expand this 5 minus 3i whole cube in the by using the identity z1 minus z2 whole cube is equal to z1 cube minus z2 cube minus 3 z1 z2 into z1 minus z2. So by using that principle we write this, and after this we can have this value. Okay, now example 4. Express this in the form of this a plus ib. So we'll multiply stepwise. Minus square root 3 into 2 square root 3 becomes minus 2 into 3, that is minus 6, and minus 3 minus square root 3 into minus I becomes plus square root 3i, and minus square root of minus 2 into 2 square root 3 becomes 2i square root 6, this, and now this becomes square root 2 into I square, so minus sign, and ultimately we'll get minus 6 plus square root 2 plus square root 3 into 1 plus 2 into square root 2i. So we see that we can solve the examples by using the identity. So friends, let's define the modulus and the complex conjugate of a complex number. So suppose you are given complex number z is equal to a plus ib, and you have to find the modulus and the complex conjugate of this number. So modulus of this number can be given by modulus of z is equal to square root of a square plus b square. That means square root of the real number a square plus real number b square, and the complex conjugate can be given by denoted as z bar is equal to a minus ib, that is z bar is equal to a minus ib. So note this. So modulus of this complex conjugate is equal to square root of a square plus b square, and complex conjugate is equal to z bar is equal to a minus ib. So this is the definition of the modulus and the conjugate of a complex number. You can utilize this definition for solving any kind of problems related to complex number. So suppose you are given the 3 plus I and you have to find the modulus, so that will be equal to square root 3 square plus 1 square, that is equal to square root 9 plus 1, that is square root 10, and complex conjugate will be square root will be equal to 3 minus I. So similarly we can solve for 2 minus 5i. Now observe that multiplicative inverse of the non-zero complex number is given by z minus 1 is equal to 1 by a plus ib and can be written as this. So that means z into z bar is equal to modulus square of z. So remember this identity. For any two complex number z1 and z2, we can have modulus of z1 into z2 is equal to the product of the modulus of z1 and z2. Modulus of the ratio of the two complex number is equal to the ratio of the modulus of the each number, provided the denominator should not be equal to 0. Similarly, we can have the complex conjugate of the product of two complex number is equal to the product of the complex conjugate of each individual complex numbers, and this identity also. So you can solve example 5. Find the multiplicative inverse of 2 minus 3i. That means you have to find the number inverse of the 2 minus 3i, so that the multiplication of these two numbers give one identity, multiplicative identity. So that will be given by 1 by 2 minus 3i. So z is given. So z bar is equal to 2 plus 3i. Therefore, we have to find the multiplicative inverse. So multiplicative inverse means, that means z minus 1 is equal to 1 by z. We have to find. So simplest way is this: 1 by 2 minus 3i, that can be written as the 2 plus 3i divided by 2 minus 3i into 2 plus 3i, and the denominator will give 2 square minus 3i whole square, that is equal to 13. So we have this number. But by the definition, we can also solve this problem by z into z minus z minus 1 is equal to z bar divided by modulus of z square. So anyway, you can solve this problem. Now the example number 6. Express the following in the form of a plus ib. So you are given the problem in terms of ratio, and you have to find the solution in form of the a plus ib. So you will simplify this problem by multiplying both numerator and denominator by 1 plus square root 2i. So by this, so denominator will be 1 minus square root 2i whole square, and the numerator will be given by this. So after simplification, you will get 3 plus 6 into square root 2i divided by 1 plus 2, and that means this. So you will get the simplified form of the complex number, that is in terms of a plus ib. Now you have to find the I to the power minus 35 in terms of a plus ib. So you know that this can be written as this, and you will simplify in terms of I square. So after writing this in terms of I square to the power 17 into I, you will get this 1 by minus I into, so because this gives minus 1, so it will be minus, so 1 by minus I. So multiplying both numerator and denominator by I, so you will get I by minus I square, that is I. So this can be written as 0 plus I. So similarly, practice the exercise 5.1, and if you have any problem, let me know in the comment. So suppose you want to solve this in the form of a plus iv. So how we can do this? So multiply this 5 into I square into minus 3 by 5. So I square is equal to minus 1. Minus 1 into minus is equal to plus. So plus 5 into 3 by 5 is equal to 3. That means this is equal to 3 plus 0i. Similarly, you can solve others also. So this is similar to this I to the power minus 35. Solve this. This can we also solve. Very simple. So solve this. If you have any problem, let me know. Now we will discuss about the complex plane or Argand plane and its polar representation. Friends, you already know that we can represent any point in the two-dimensional or three-dimensional plane of x, y and z axis, and I have given the video lecture on this topic, and you can watch by visiting the description box, and I will also provide the link in the upper right corner of this screen. So let us discuss what is Argand plane and polar representation of any point in terms of the x and y axis, that means real axis and imaginary axis. So Argand plane, in case of Argand plane, the x axis is known as the real axis and y axis is known as the imaginary axis. Okay, so any ordered pair of real numbers represents a point in the x axis and y axis plane, xy plane. Okay, and vice versa. Similarly, any complex number ix plus iy which corresponds to ordered x, y can be represented geometrically as the unique point p x y in the xy plane and vice versa. So suppose you are given the complex number such as 2 plus 4i minus 2 plus 3i 0 plus 1i and so on, which corresponds to the ordered pair this and have been represented by a, b, c, d, e and f in this figure 5.1. So you can see that these complex number can be represented geometrically in the xy plane, and this plane is known as the complex plane or Argand plane. So let us discuss this in detail. Suppose you want to represent x plus iy in the complex plane. So firstly you will write this complex number in terms of the ordered pair x, y, and you will measure this x value on the x real axis and the y value on the y axis, and where this meet will represent the p, and this OP distance can be given by the modulus of this complex number, that means square root of x square plus y square. The point on the x-axis corresponds to the complex number of the form a plus i0, and the point on the y-axis corresponds to the complex number of the form 0 plus ib. As I already told you that x-axis is known as the real axis and y-axis is known as the imaginary axis. So the representation of a complex number and its conjugate in the Argand plane can be given by pxy and qx minus y. That means in the complex plane, point Q is the image of the point P on the real x-axis. Now the polar representation of a complex number. So I think you can represent any given complex number on the complex plane by following these guidelines, that you have to find the x ordered pair and you have to calculate this distance by x square root of x square plus y square. Now what is the angle? This angle we can find. This is known as the argument of the complex number. So let us discuss that. Polar representation of a complex number. Let the point P represent the non-zero complex number z is equal to x plus iy. Let the directed line segment OP be of length r and theta be the angle which OP makes with the real axis. Now we note that the point P is uniquely determined by the ordered pair of real numbers r and theta. So here in the polar representation, the ordered pair is the r and theta. That here r is the distance of point P from the pole, where O is the origin, and in case of the polar representation it is called the pole. So the distance OP is the r and theta is the angle which makes OP with the x-axis, and this representation is called the polar coordinates of the point P. Now we can see that this distance is equal to r sin theta, and this distance OX is r cos theta. That means x is equal to r cos theta and y is equal to r sin theta. Therefore z can be written as z is equal to r cos theta plus I r sin theta, and this is known as the polar form of the complex number, and that is also can be written as r into e to the power I theta, because e to the power I theta is equal to cos theta plus I sin theta, and distance r is the modulus of z, that is equal to square root of x square plus y square, and theta is called the argument or amplitude of the z. Now it is very important to note that for any complex number z not equal to 0, there corresponds only one value of theta in the complex plane, that is equal to theta greater than and equal to 0 and less than 2 pi, which can also be written as theta greater than minus pi and less than and equal to pi. We shall take the value of theta such that minus pi less than theta less than equal to pi, that is theta is greater than minus pi and less than and equal to pi, called the principal argument of z, and it is denoted by the argument z unless specified otherwise. So you can see in the figure 5.5 and 5.6, for both the cases, for theta lying between 0 and 2 pi and theta lying between minus pi to pi. So we can see that by diagram, for this case the P point lying in the first coordinate, for this case also P point lying in the first quadrant, and for this case P is lying in the second quadrant, and here P is also lying in the second quadrant. Now in both cases the orientation of angle was the anticlockwise, but here you can see that orientation of the angle is anticlockwise, while in case of this the orientation of angle is clockwise. That is the difference of representation here also. So you should note that for the angle representation in terms of 0 less than equal to theta less than 2 pi, we for this third and fourth quadrant there is a difference of orientation of the angle. Now example number 7. Represent the complex number z is equal to 1 plus I into square root 3 in the polar form. So you are given a complex number z is equal to 1 plus I square root 3. So firstly you will compare this with z is equal to x plus iy, and you see that x is equal to 1 and y is equal to square root 3. So what you will do for the polar form, you will find theta and r. So theta is equal to square root x square plus y square. So this will give r is equal to square root x square plus y square. So r is equal to 1 square root 1 square plus square root 3 whole square. That means square root 1 plus 3. That means r is equal to 2. And theta is given by here x is equal to r cos theta, y is equal to r sin theta. Therefore tan theta is equal to y by x. So tan theta, that means y is equal to square root 3 by 1, theta is equal to therefore pi by 3. So in this way we can calculate the argument of the complex number. Thus we can represent z is equal to 2 e to the power I pi by 3 or 2 into cos pi by 3 plus I sin pi by 3. Whatever form you want to write, you can write. Similarly, you can do this for the example number 8. Use this concept, you will easily be able to solve this. Now exercise 5.2. So you have to find the modulus and arguments of each of the complex number. You can do this very easily as we had discussed earlier. Now the quadratic equation for the complex numbers. So you know that for a given quadratic equation ax square plus bx plus c is equal to 0, the roots can be given by x is equal to minus b plus minus square root b square minus 4ac by 2a, where square root b square minus 4ac is the discriminant, and if it is less than 0 then the roots or solution will be complex number. Okay, so the square root of negative real numbers of this in the set of complex numbers, we can give the roots by minus b plus minus square root 4ac minus b square into I by 2a. So for the b square minus 4ac less than 0, we will use this. And also you know that the any polynomial equation of the given degree will have the that much number of solutions or square roots. That means if you are given the polynomial of 2 degree, then you will have the 2 square roots. If there is a polynomial of 1 degree, that is simple linear equation, it will have the 1 root, and if it is of 3 degree, then it will have the 3 roots. So generally a polynomial equation of degree n has the n roots. So solve the x square plus 2 is equal to 0. We have to solve this. So by comparing this ax square plus bx plus c is equal to 0, we see that a is equal to 1, b is equal to 0 and c is equal to 2. By substituting these values in the formula, this we can get that the solution will be equal to plus minus square root 2i. Okay, because this is very small equation, so you can directly write also, but by application of the proper formula you can also solve it. Now solve x square plus bx plus 1 is equal to 0. So you can utilize this formula. So exercise 5.3, solve each of the following equations. X square plus 3 is equal to 0. So x square is equal to minus 3. Therefore x is equal to square root minus 3. That is equal to square root 3i. Okay, we will take only the plus sign. Similarly, you can solve these all equations, no problem. Just practice it. Miscellaneous examples are given. Find the conjugate of this. So for finding the conjugate of complex number in terms of given in terms of ratio, you have to firstly simplify in terms of a plus ib. After that you can easily get the conjugate of this complex number. So for simplification you will multiply this. After multiplication you will get this form. Therefore conjugate will be given by the plus sign. That's simple. Example number 13. Find the modulus and argument of the complex number. So modulus and argument. So firstly we will solve in terms of solve for the a plus ib form. So for that you will multiply this 1 plus I by 1 plus I. So denominator will be 1 minus I square, that is equal to 2. That means 1 plus I whole square divided by 2. So you will get this, that is equal to this I. So modulus of this will be equal to square root of 0 square plus 1 square, that is equal to 1, and argument theta is equal to tan inverse y means 1 by x 0, that is 5, theta is equal to 5/8, theta is equal to 5/8, because tan pi by 2 is equal to infinite. Okay, hence the modulus of 1 plus I divided by 1 minus I is 1 and argument is pi by 2. Similarly you can calculate for this 1 by 1 plus I by multiplying the numerator and denominator by 1 minus I, and after simplification you will get 1 by 2 minus I by 2. Therefore r cos theta is equal to 1 by 2, r sin theta is equal to minus 1 by 2. Therefore tan theta is equal to minus 1. Therefore theta is equal to minus pi by 4. Similarly you can get the argument is equal to r is equal to 1 by 1 by square root 2. Okay, so you get the result. Now example 14. If x plus iy is equal to a plus ib divided by a minus ib, prove that the x square plus y square is equal to 1. That means you have to find the square of the modulus of this. So firstly what you will do, you will simplify this in terms of a plus ib. That means a plus ib form you will simplify it. So for that you will multiply the numerator and denominator by a plus ib, just the reverse of this, inverse of this, or you can say the complex conjugate of the denominator. You will multiply both numerator and denominator. After simplification you will get this and this. So you can, so this is x plus iy and hence the x minus iy is equal to this. So you can get x square plus I square is equal to x plus iy into x minus iy. Therefore you get the result is equal to 1. Find real theta such that 3 plus 2i sin theta by 1 minus 2i sin theta is purely real. So for that you will simplify this in the form of a plus ib, and you will take the only real part. So firstly what you will do, simplify this by multiplying the numerator and the denominator by 1 plus 2i sin theta. So you get this 3 plus 6i sin theta plus 2i sin theta minus 4 sin square theta, 3 plus 8i sin theta minus 4 sin square theta by 1 plus 4 sin square theta. So separating the imaginary and real part you will get this. That means as per the problem this is purely real. That means the imaginary part should be 0. So equating this imaginary part equal to 0, then 8 sin theta by 1 plus 4 sin square theta is equal to 0. This implies that sin theta is equal to 0, as 1 plus 4 sin square theta can't be 0. Therefore theta is equal to n pi, where n is the integer. Now convert the example number 16. Convert the complex number in the polar form. So for this you will simplify firstly in form of the a plus ib. For that you will substitute the value of cos pi by 3 and sin pi by 3. So cos pi by 3 is equal to 1 by 2 and sin pi by 3 is equal to square root 3 by 2. So you will get this. After simplification you can get this, right? That means r cos theta is equal to square root 3 minus 1 by 2 and r sin theta is equal to square root 3 plus 1 by 2. Therefore tan theta is equal to square root 3 plus 1 by square root 3 minus 1, and after simplification you will get square root 3 plus 1 into square root 3 plus 1 by 3 minus 1, 3 plus 1 plus 2 square root 3 by 2, that is 4 plus 2 plus square root 3. We can calculate theta is equal to tan inverse 2 plus square root 3. Now the value of r can be calculated by squaring r cos theta and r sin theta and then adding them. So you will get r square is equal to this. So r is equal to square root 2. Therefore we can write this in form of the polar form by r cos theta plus I sin theta. that is this value. So where theta is equal to tan inverse 2 plus square root 3. So miscellaneous exercise on the chapter number 5. So please solve it, and if you have any problem, let me know in the comment. I will help you. Now friends, summary of this chapter. So in this video lecture we talked about the complex number, their real and imaginary parts, their representation on the complex plane, the polar form of the complex number, and their mathematical properties of additive and multiplication. So a number of the form a plus ib, where a and b are real numbers, is called a complex number, where a is called the real part, b is called the imaginary part of the complex number. So if z1 and z2 are the two complex number, then their addition can be written as this and multiplication can be given as this. For any non-zero complex numbers, there exists the complex number of the form this, that is called the multiplicative inverse of z, such that a plus b into this is equal to 1. For any integer k, I to the power 4k is equal to 1, and I to the power 4k plus 1 is equal to I to the power 4k plus 2 is equal to minus 1, and I to the power 4k plus 3 is equal to minus I. So conjugate of the complex number z is equal to a plus ib can be given by z bar is equal to a minus ib. The polar form of the complex number can be written in this form, where r is known as the modulus of the z and theta is known as the argument of z. The value of theta such that theta is greater than minus pi and less than equal to pi is called the principal argument of z. Any polynomial of n degree have n roots. The solutions of the quadratic equations where a, b, c belongs to the real number can be written in terms of x is equal to minus b plus minus square root 4ac minus b square I by 2a, where discriminant is less than 0. So friends, these are the things which I wanted to discuss in this video lecture. Hope you enjoyed this video lecture and learnt about the complex number and the complex number systems, their different mathematical properties. Friends, if you like this video, please like, share and subscribe the Sciacademy channel. And if you have any doubts, query, please comment. I will solve your problem. So thank you friends.